Okay, so welcome to the SWOT data inversion and assimilation working group. This is intended to be pretty informal, but we will have a recording. Today we have Florian Le Guillou, who's going to talk about mapping SSH with VarDyn, um, and I'll let him take it away, and then we'll have time for discussion afterward.
Yes, thank you, Sarah. Hello everybody. So I'm Florian Le Guillou from Datlas, and today I'm going to present VarDyn. We call it VarDyn, but if you want to say VarDyn, it's okay for me. To map like sea surface height field from Nadir and SWOT altimeters. So it's a presentation that is after the one from Maxime Balarota last month, who presented the MIOS operational level 4 product. This one is more like experimental, so it's we don't have like um, kind of end product to present now. It's more like some attempt and still a work in progress. So I'm really happy to have any feedback from you. So this work is has been done in collaboration with other people from Datlas and Maxime from CLS and Emmanuel Com from IGE. So I'm starting now. So I'm going to present the method first, and then I will show a global setup with some performances. And then I have two kind of experimental studies, ongoing studies about internal tide estimation and multi-sensor estimation. I hope not to be too long. If you have question, I think it's okay. You can ask me even if I'm presenting. I think it's more it's more like it's better to have kind of a discussion more than a formal presentation. So don't hesitate to stop me. Just a slide about a bit of context. So here we speak about mapping SWOT, like mapping altimeters to have graded products that are regular in space and time. So we start from level 3 data from SWOT, and we aim to have level 4 data. So as you can see here on the right, the maps. So this is from VarDyn in the Gulf Stream region. So we have a bunch of mapping methods. And I like to present the different methods like following these two axes. So like more you are in the left, more you have like a data driven method that are more robust. And more you are to the right, you are more like physics based or like conventional data simulation. So Maxime presented last month the MIOS system, which is really like the data driven because like we don't have any dynamical models or like any AI learned from simulation. It's really like based on data. So this is kind of the left side of the method. Then on the right side, you have like conventional data assimilation algorithms. So like Mercator, for instance. So I think it will be next talk for the next months. So this is like giving a better view of the ocean dynamics. It's way more realistic, but the main drawback of this kind of method is they are 3D or like 4D in time. And so you have many degrees of freedom. And if you only constrain with like surface data, like SWOT, then you tend to have like a field at the surface, which is less accurate than like a conventional interpolation method that focus on the surface. So even if it's more realistic, sometimes the mapping performances can be reduced at the surface due to the complexity of the models. So we have then some hybrid methods. So these are like for instance, VarDyn, which is a data-driven dynamical um, interpolation, and we have also another method, the 4D net, which is a AI deep learning based method. So it basically learned on high resolution and complex simulation as for the Mercator system, but instead of doing like conventional data simulation, it tries to focus on the surface by learning the surface from the data and from the simulation. So that's why it's like kind of a hybrid method. So here in this presentation, as you know, I will speak about the VarDyn methods. So the main strategy is to use reduced surface focused models to match the observation density, so the surface, which allows to have a fully controllable system and fully data driven, because like the model is really used as a weak constraint in the data estimation system, and it's simple enough to really focus on the data. So I will open this box here. So for mapping the sea surface height fields, the main strategy is to use the quasi-geostrophic model. So basically, so it's a one layer and a half. So it's really simple. We know it's not predictive, but it's really relevant for the like a dynamical constraint as shown since it's it has been tested and shown for like more than 10 years now in this context, and I think it's really robust, and we kind of know how it works and how to constrain it to really help the mapping procedure. So I recall here the main equations of the model. So eta here is the sea surface height, q is the potential vorticity, and this equation here states for the conservation of the potential vorticity along the geostrophic flow. In the conventional model, we have a zero here, but as I was saying, the QG is really not predictable. So the trick here is to add this term, the epsilon here, which is a flux, which represents the error of the QG model. So by this term, we can actually bend the QG trajectory to match the observations. So basically, we can say that the full trajectory of sea surface height, so in space and time, is given by model integration from like a initial state and the forcing fluxes epsilon. So this is the dynamical constraint. Then one main aspect of the VarDyn methods is to use reduced spaces in order to reduce the number of degrees of freedom. Because here you have, so here it's 2D in space, and the fluxes are 3D space plus time. So you have many degrees of freedom. So the thing is to use wavelet basis in order to project this physical field into latent space and to perform the assimilation in this reduced order basis. So basically, it's the same strategy as MIOS. We really use kind of the same space, like reduced space or wavelets that are that have decorrelation time. Basically, like more you have large, like the large scales have longer time scales, and the small scales have smaller time scales. In that sense, you can like replicate the variability of the ocean surface with this kind of construction of the basis. So then, we can project this physical variable into the basis, W, which is known, which is prescribed, and the coordinates of the basis, psi here, they become our control vector. So all the 4D var minimization is done in this reduced basis. And it has the advantage to have a diagonal background matrix because the components are built to be independent from each other. So at the end, we have like we find the optimal psi vector that minimizes this cos function, and we can build again the optimal trajectory of sea surface height to get the level 4 product of this VarDyn method. So this is the method. We can come back after to that if you have questions. I can give some details more. And yeah, now in terms of more like engineering work, to produce a global product, we have followed this strategy. So using tiles, so space and time tiles. So 50 days in time, 50 degrees in longitude, and 12 degrees in latitude. So here you have the drawing of all these tiles. So they overlap in order to have at the end a smooth reconstruction in space and time. And so we've done that for two main reasons. One is for time consumption, like time computation time. So the main strategy is to use like to perform all these styles in parallel, so that we can launch in multiple CPUs and GPUs. And one other reason is more linked to physical laws. It's like as we use a spectral QG model, then all the parameters have to be constant in space. And these parameters are the Coriolis parameter, the uh, Rossby radius, and the grid spacing. And we know like these parameters, F and L, vary in space, even in time. So the idea to use tiles is we can take into account this spatial variability of these different parameters. One other detail is that as you might know, the QG is not working at the tropical band. I mean, at the equator line is not defined, and at the tropical band is not relevant, meaning that the assumptions are not held. So the basic thing here is just to use like an identity model in the forgiver. So we don't use any dynamical constraint in the tropical band. And then, yeah, as we have all the results of the tiles, we build again the maps by space and time interpolation using Gaussian kernels. And at the end, we have numerical resolution in time of 6 hours and in space of 0, 1 degrees longitude, latitude. So you have here like an example in the year 2019 of the VarDyn product. Then for the performances, so it's similar as what Maxime showed last month. We use like an independent altimeter to compute the errors between the maps and this uh, independent altimeter. So in our case, we use the Sarah Altica altimeter. The input dataset are all the other altimeters, including SWOT, and we have tested it during the year 2024. So when we have kind of all these errors, like the comparison between the independent altimeter and the maps, then we can compute some statistics. So here I'm showing the root mean square, like over 1 degree by 1 degree boxes. It's averaged over 1 year. And when we have that, we can compare these error maps between different products, and we can compute the reduction of the variance of the different mapping products. So here it's just like an example of like, so it's for the Nadir constellation, and it shows the reduction of the errors brought by VarDyn compared to MIOST during 1 year. So in blue, so it's like between 10 centimeters square minus and plus. In blue, it means that VarDyn like does a better job than MIOST. So it's kind of clear here that it's almost blue like everywhere, even dark blue in the highly energetic regions. It's reddish in the equatorial band, and this is like expected because we don't use any models. So it's kind of similar as MIOS, but MIOS uses a special radius basis for the equatorial dynamic that VarDyn doesn't use. So that's why like MIOS is better. But we are working now into like implementing non-linear shallow water in the tropical band to replace the QG model in order to have better performances in the tropical band. But still, in all the mid latitudes, We have very good performances using VarDyn compared to MIOST. So this is only using Nagier missions, but if we include SWOT, no, yeah, sorry, I just wanted to show just like a qualitative results. So this is over the Gulf Stream, and it shows the VarDyn relative velocity sliding on top of the MIOST one. And so yeah, we can clearly see that the main outcome of the VarDyn is to have like a really good consistency in space and time of the structures. We can clearly see like it's kind of out of a dynamical model, but it's really data driven. So it's really like the scales observed here are really in the good location in space and time. Um, so yeah, this was just to show some qualitative results. And now I'm focusing on on SWOT data. So on the upper left, you have the VarDyn product only using only the Nagier missions. On the right, you have the sea surface height from SWOT, anomaly from SWOT. And below is the residuals of SWOT and the Nagier products. To the left, if we use the raw SWOT data, and to the right, if we correct from a large scale bias estimated by the MIOST algorithm. So I think Maxime talked about that last month, but it's really key to have good performances. So it's just like a way to say to the community, if you look at the SWOT data, I think it's really relevant to correct for this large large scale bias. But if I stop here, for instance, you see like here is kind of all blue. So this is really like a large scale bias in the raw data. And when you correct it, then you just have the small scale residuals, which are really physical scales. And these scales will allow to improve your mapping system. But if you include all these large scale bias, then it's really hard to make a good data simulation run. Like for me, it was really like key to correct this large scale bias. So yeah, just a way to say it again. Okay, and now in terms of performances, so this is really new. Actually, it's from today. It's only 2 months of data, so the statistics might be more clear when using 1 year. But this shows the improvement brought by SWOT in the VarDyn system compared to the Nigeria's constellation. So in blue, it means that SWOT improved the mapping quality. So yeah, again, it's 2 months, so I think it's a bit patchy, but we can clearly see that it's more blue than red. But yeah, it's still like a work in progress. Like I really want to show it when we have 1 year, but I think yeah, it will be just more defined. Like the statistic will be more located, and I really expect to have kind of a good improvement in the like western boundary currents and maybe like a lower improvement in the low variability region, and especially actually in regions like here or here or here where you have like a strong internal tide dynamics, because SWOT is able to observe this internal tide dynamics, but it's not taken into account with the QG system in VarDyn now. So yeah, actually, it's my transition to go to the next section. So yeah, you might know that SWOT observes internal tides and internal waves in a more general context, and this is really like a challenge. So it's super interesting for many scientific studies. Like people who are looking to these processes are super excited, but in the mapping community, then it's really like a challenge because it's small scale signal observed by SWOT, but they are like super dynamic, meaning like they have like really small time scales, like of several hours, and with the low time revisit of SWOT, which is basically 10 days, then it's really complicated to map these processes. So it's kind of a biggest challenge, and I think it's why we don't see like a huge improvement in the mapping quality with SWOT, is because we have this internal tides that limit the accuracy of the mapping methods when you reach the scales of these processes. So basically 100 kilometers for the first mode of internal tides. Um, so we are working on this, trying to adapt the method to take into account these processes. So I'm going to speak about that now. So this is in the context of the PhD from Valentin Belman-Laponaz, who is working with us now for several months and who is still continuing this study. So he has implemented like a dynamical constraint specific to the internal type dynamics. So we still have the QG for the balance motion, BM states for balance motion, and now we add a new dynamical constraint, shallow water model. So it's a linear shallow water model. You have the pronostic equations here. Um, but the strategy is to use like specific forcing to replicate really the internal type dynamics. So this forcing are open boundary conditions, eta b here. We have a generation term inside the domain. And we have also this HE parameter, the equivalent depth, which simulates the modulation of the internal tide field due to stratification and due to balance motion also. And if we combine the two, then we have the space and time trajectory of balance motion and internal tides, which are given by the model trajectory, model integration of these control variables. And then we follow the same process. So we use covariance model for each parameters. So we have like a reduce basis operator, and we do the minimization in this reduced space, and then we get the optimal trajectory using the optimal control vector. And so at the end, starting from SWOT data and Nadir data, we get the maps of balance motion and first mode of internal tides. So this has been tested within the PhD of Valentin for the Kelval phase because it's like the most like it's the easiest setup, let's say, because we have a high temporal frequency of the SWOT data. So if it's not working with the Kelval phases, then it's useless to go through the science phases. So that's why we started with this. And I'm going to show some results. No, first, yeah, just like as an illustration, I wanted to show this control variable. So this is the generation term here. So we control the phase of the internal tide generation, like the barotropic tides. So here is an example in Hawaii, I think, so that we can generate internal tides from this. Then we have incoming waves. So same, we control the characteristics of the waves entering the domain. So here we have just like an example of like if we like make entering random waves in all the borders. We have that kind of field. And then I think the most important parameter is this one is so the HE field, which allows to modulate the wave phase speed in order to like it's like really like a physical phenomenon. Like when you have like an anomaly of density of stratification, then you have a modulation of the wavelength. So this states for the interaction between balance motion and the internal tide field. And so all these parameters are controlled by the data assimilation, even if they are not directly observed, they are controlled thanks to the weak constraint for Diva. These are results in two regions of the Caval phase. So to the left, you have the California crossover, and to the right, you have like the track offshore the Amazon River in the Amazon current. And what we do here is we use 20% of the subset of SWOT data in order to make the validation. So we use only SWOT and Nadia data. So 80% of SWOT and the Nadia constellation as input of VarDyn. And we compare with the MIOS plus Hret products. And also we have two run. We have a run only using only the QG model, which is like the initial configuration. And we compare when we use the shallow water models. And here is the mean error over the 20% subset of SWOS. And here is the special variation of the improvement by the shallow water. So when it's blue, it means that we reconstruct internal tide fields which are in phase with the independent data. So we do like a good job. So in the Amazon region, it's all blue, so it's kind of super encouraging, and it's like improved like around 30% of the mapping quality in terms of average errors. But in the California clearance, it's more patchy, and the reason of that are not super clear now. We don't really know why we have that patchy performances. Even if we see the global metrics, it's still good, but I think it's not super. I mean, we can do better. And one way to do better actually is to improve the dynamical constraints. So it's what I show here. So I think like seeing the time, I will try to go fast on it. But if you have questions after, can go back. But I might kind of skip some details. But so to go to the science phase, so to use VarDyn with the internal tide estimation during the science phase. We think it will really be complicated with this configuration I just showed, because like we have many degrees of freedom, many parameters, and no one is directly observed. So like if you don't have like a big density of data as for the cable phase, then it's really hard to control the system. So one way to reduce the number of degrees of freedom is to improve the dynamical constraints. So for that, we work with the NoELA to improve the dynamical constraints, and basically we couple the QG with the shallow water, because for now they are not coupled. They are just seeing the same observation, but they are not directly coupled. So what we want to do is to create a new model, like a QG shallow water, which like use QG assumptions for the balance motion part, and shallow water dynamical framework for the internal tides. So for that, we use like we go back to the simulation world, and we use this simple simulation that propagate like the first mode of internal tides at the southern boundary, and it propagates over like a balanced jet, simulating like the western boundary currents. And so as it goes through the jet, it gets non-stationary. So meaning that the phase is moving in space and time. Here it's a 12 hours tide. So, and we have one frame every 12 hours. So that's why you don't see the tide like oscillating. We always see the same phase. So when the phase is moving, it means that it's a non-stationary field. So more it's non-stationary, the more it's complicated to estimate from SWOT, because like we need really dynamical method to simulate this kind of non-stationary fields. So yeah, we start from this setup, and I just extract one snapshot every 10 days to use as synthesized SWOT observation. So yeah, one observation every 10 days, and we try to separate and map the balance motion and the internal types from these fields. And this is the initial configuration with the shallow water, like the linear shallow water model. And as I was saying, HE is the main parameter to modulate the phase of the field. Actually, it's a main parameter to replicate the coupling between the balance motion and the internal tides. And what we do now is we add three new terms that replicate, that simulates the coupling between the balance motion and the internal tide field. So we have additive terms here and here, and we have like delta HE that we add here to make the modulation coupled with the balanced motion. So all these orange terms, they are calculated from the balanced motion field, so the velocity field for the big U and the sea surface height field for the delta HE. So here, these are functions of the vertical modes of the first baroclinic vertical mode and the barotropic mode. So I'm not showing the equations of this function because it's a bit complicated, but it's actually, if you know the vertical mode decomposition, it's kind of easy to get it. And alpha is just one parameters that gives the relative energy between the barotropic modes and the baroclinic modes. And this becomes our main control variables actually, and it's super smooth field, way more smooth than the HE we tried to uh, invert before. So yeah, instead of estimating HE for all the pixels in space and time, now we just estimate alpha, which is way smoother, way more smoother, and we add two other terms also. So this is the setup, and these are the results. So we use 10 days observations, like 2D observations every 10 days. You have the reference field, the IT field here. Here you have so this new coupled shadow watcher using the true balanced motion. To the middle, you have the uncoupled shadow watcher, so the initial configuration we had before that we tried to use for the Calval phase. And to the right, you have the coupled QG and shadow watcher, so the new system we want to implement for the real data. So basically, we see that yeah, maybe I can just show the statistics of the root mean square errors. So more it's red, more we make like errors. So it's in percent of the IT fields. And we see like for the uncoupled QG shadow watcher, like when it's like non-stationary, so just after the jet, it's where we have like we get like the most of the errors. But when we use the coupling, now we really reduce this kind of errors. And what is really interesting is like coupling with the QG is really similar than just using the true field for the balance motion. So yeah, it's just a way to say that the method is working, and we are quite happy for like what we can win from this new implementation of the dynamical couplings. In terms of balance motion reconstruction, so to the left, you have the balance motion reconstruction. Here you have the QG only method, so the initial VarDyn method that we test with SWOT globally during the science five. So the first part of my talk. And you see that we see the internal tide aliasing. So the internal tide projects onto the ballast motion, and that's why like we can't reach really small scale mapping methods with SWOT is due to this like internal tides that project onto the balance motion field. Then we have the uncoupled QG shadow water, so the initial configuration with the shadow water, and then with the coupled shadow water. And when we look at this time, the time evolution of the errors, so blue is the QG only VarDyn, and then orange and green are for the copper, like for the when we add the shadow water for the internal tide estimation, and we see that coupling the two QG and shadow water allows to have reduced perform like improved performances even for the balance motion. So it's not just for having like accurate internal tide estimation; it's also for having a better balance motion estimation. So these are really idealized experiments, and now we are working in a more realistic OSSC using like a complex simulation and science phase SWOT sampling to validate this strategy. And then the plan is to go for real data and to include this into the VarDyn system to have enhanced performances with this new coupling method. And just to finish, I wanted to add something about the multi-sensor data assimilation. So yeah, this is the famous figure from the paper of Matasher, showing that the small scale observed by SWOT are also observed by tracer satellite observation. So here you have like an example of this small cyclonic eddy observed by temperature and chlorophyll data. And so we know that the sea surface height is is dynamically coupled with the tracers, and this is known from the physics. It's based basically on the geostrophic tracer advection. And we have worked now for some months to try to include this dynamical constraint into the VarDyn system to have like a combination of assimilation of sea surface temperature, salinity, and sea surface height into like a coupled model in order to have at the end output like a high resolution output of all these variables. So it's what I show here. I will not go into the details, but basically we still have the QG model for the sea surface height dynamics, and we use the tracer dynamics model here, and we estimate the forcing terms into the data and into the data assimilation process. So we start from level 3 data, sea surface height, temperature, and salinity, and then we reach the level 4 high resolution product. This is just a test in the Gulf Stream region, in the North Atlantic region, and it shows the improved performances in blue when we assimilate sea surface temperature and salinity for the reconstruction of sea surface height. So yeah, it's just like it's a bit red also. So like I think there are some like tuning to do, but we are still happy to see that we can do more things by combining different kind of data, even with SWOT, to make at the end like the best mapping as possible, and also to have a really good like this, also to have a good consistency between the different variables, because at the end you have the salinity, temperature, and sea surface height that that have seen the same physical models, so they are consistent, and so you can use even different like you can compute high value product from this combination of different variables. This is just an illustration of the field we can get from the VarDyn product compared to operational products. So this is the sea surface salinity, and then you will see the temperature. So this is from the operational product, microwave product, and this is what we can get with the VarDyn. And so yeah, as I was saying, like sea surface temperature, salinity, and height are really consistent together. So it's also a way to enhance SWOT is to like yeah use like after like a combination of different variables to make like scientific studies. So these are the conclusion. So I've shown the global VarDyn product using the Niger constellation, which shows like a clear improvement of the performances compared to MIOT, especially in the western boundary currents. We have region no, now it's not regional, it's like a global VarDyn product using SWOT that demonstrate like a moderate improvement compared to the Niger product. It's still good, but it's moderate. And we think that one way to improve that is to focus on the internal tide mapping. So I just showed like some studies we've done on this topic. And also one way to enhance SWOT and to yeah to make it used effectively is also to combine with the different tracer data into the data simulation procedure to have at the end high resolution field physically consistent. So I stop here and I can answer some questions if you have. Thank you.
Thank you very much. This was great. Questions for Florian? While people are thinking, let me just ask a really basic question about the VarDyn product. Is it readily accessible for people who want to look at it or compare?
No, as Maxime was saying last month, we plan to make it accessible before summer. So now, yeah, I have 1 year using the Nigeria constellation. I have only 2 months using SWOT because it's just like
Mhm.
it was just like a small test. But now I'm quite satisfied. I will run the 2 years production of the product, and so yeah, I think in the following weeks we will upload it to the Aviso system to make it available for everyone.
Great. I see Spencer has a hand up.
Yeah, so yeah, very nice work. I really like this approach. I guess I was trying to wrap my head around. So you have a generation term for the internal tides,
Yeah.
and then you allow them to come in from the sides, and then you're allowing the stratification to change as well. But how do the internal tides disappear, right? Like, how are they dissipated? Is there a term that does that, or is the generation term dealing with that? What's the situation?
No, like for now, the only way to exit the energy is from the open boundary
Okay.
system. So like you can make wave enter, but you can also make wave like going outside of the domain. And this is classical in the model community. Like you have ways to implement open boundary conditions. So it's like a radiative boundary condition that allows to either make wave enter or exit the domain border. So yeah, for now it's the only way to make the wave going outside of the domain. But if we want, for instance, to have like a basin scale reconstruction, then we don't have any more open boundary conditions because like it's just like basin scale, so we have just land. So we will have to think about a strategy to make the like sync terms into the dynamical equations. So for now we have a source term with the generation of tides, but we will have to add like another term to make the field disappear sometimes and somewhere. Otherwise, the energy will just grow infinitely. So we have to find a clever way to make the wave disappear because like in the real life, the first mode is going into the second or third mode
Yeah.
physically. So we have to implement a way to make it happen without resolving the second or third mode. So yeah, we are thinking about it.
Yes. Yeah. I think that sounds like a good plan. Yeah.
Mhm. Yeah.
Other questions? Can I ask about resolution?
Hmm.
So you show these beautiful images where the VarDyn resolution clearly looks better than the resolution of the gridded products. Um, but of course, some of that could just come from the resolution you're mapping onto. What do you think the effective resolution is?
Yeah, I'm sorry, I don't have the plot, and it's really not to hide it because it's good. But yeah, basically, yeah, this is with SWOT, but let's show with the VarDyn. Basically, the improvement is really like occurring at small scales,
Mhm.
so it tends to increase, like to reduce the effective evolution. And so basically in the western boundary current, we are like around 90, 100 kilometers effective resolution, whereas the mirror system is more like about 120, 130. So we have like around like 30, 40 kilometers improvement with the VarDyn
Mhm.
method. And in the lower variability region, it's more kind of the same. It's a bit better, I would say, like 5 to 10 kilometers, but it's not like a huge improvement. So it's kind of
Mhm.
the similar conclusions as this figure, but yeah, I should have shown it. You're right.
Um, I'm waiting to see if there are other questions. But I also wanted to ask about surface gravity waves, which I know have a big impact on the high wave number performance in SWOT data.
Yeah. No, yeah, this like everything related to RC interactions, physics, we are not like the super like
Mhm.
experts on it, so we wait for other people to make the job. Yeah.
Sounds like as good a strategy as any.
Yeah. But I'm will be super interested if someone can find like a reduced model to take into account the surface gravity waves. But as it's super small scales, I doubt how we can resolve them without like some empirical laws or things like that. But I think looking at the sigma naught for the surface gravity waves is a way to go, I would say.
Yeah, I think there are people who have been thinking about this. Maybe Ryan has, but oh.
If no question, it's not a big deal.
Right. Speaking of the high wave number SSH signal in SWOT and also in nadir, in this system in optimizing, how you're dealing with the noise, well,
With the
with
what?
any observational, with measurement noise,
With the
from
noise.
any.
Yeah. Yeah, basically we use the like the prescribed noise from all the missions, and we have like a spatial variability of this noise. Actually, this has been computed by CLS to have like a view of the variability of the noise for each mission according to the location in the world. But so yeah, we just prescribe like just variance of the noise in the observational matrix. And we boost a bit it to take into account the model representativeness. And this is just like tuning, empirical tuning. We like, yeah, we find a good fit between the like the balance between the background matrix and the observational matrix. And I think it's kind of the similar than all the other data estimation system. Like at the end, you have to tune your matrix variances to have a good performance.
Do you allow the noise
That's
to vary in time?
No, no. I haven't tried that. No. And
for a
actually, we are
follow-up
thinking,
question about, oh,
yeah, no, no,
sorry.
no, no, no. Go.
Can I
Go
go?
ahead.
Okay. A follow-up question about the SWOT data. You said you use L3, but which one in the L3?
What kind of L3? No?
In SWOT data in L3, there, as far as I know, at least two versions of sea surface height anomaly.
Two version maybe about the resolution, the 2 kilometers of the 250 meters. I think it's no. I mean, if you are speaking about that, we are just using the 2 kilometer product because we don't foresee to estimate any scales below two kilometers. But yeah, I'm not aware of other products level 3. I mean, I'm using the level 3 distributed by CNES and CLS, and yeah, I'm not aware of other products than the resolution difference.
Okay.
Well, if there are no further questions, thank you very much. This was really stimulating, and I think it'll be great to compare what you have with all the other products people are playing with. So we'll
Yeah,
look forward to the release.
yeah. Thank you everyone for listening, and see you soon.
Yeah, thanks. Bye.
Bye.